Welcome back. This is an RLC bandpass filter problem. I've wrote it out for you because it's a lot of words. So the problem is design a series RLC filter with a quality of 5 and a center frequency omega 0 of 20 kiloradians per second using a capacitor of 0.05 microfarad. Find the time domain circuit with all component values, and B, the bandwidth, beta, and the cutoff frequencies, omega C1 and omega C2. So they're asking for the time domain circuit with all component values, but it's nice to draw the S domain circuit just to have a picture in our heads here. This problem asks you to draw the circuit explicitly. I'd like you to draw the circuit all the time. If there's a circuit to draw, you should draw it. And if there's a time domain signal that you can plot, you should plot it, like always. And most of you guys are doing that, but every once in a while, you guys don't do that. But you really should do that, because this is circuits. It's not calculus class where you just have math. There's circuits. You should draw them. All right, so this is the S domain. We have this big V of I input signal, which is a source in this case. And then there's this output signal measured across this resistor here. This thing isn't driving anything, but the last problem we did, we had a load hooked up across this V sub 0, right? Like if this were a bandpass filter in a speaker cabinet, you would connect 2 wires off of these 2 points and drive, hook the speaker up. That would be the load, which would affect the circuit. But we're not going to do that here. We just want to design this filter that's just filtering frequencies for no reason. There's no load, so we're just making the filter all by itself. Anyway, so the solution. We're just going to use various formula. And the second page of the scribbly notes has all of these formulas on it. Right? There's all these different ones here. These are the ones we're going to use. So it turns out that before we can do anything, we need really this part B stuff. So do that first. So omega 0 is 1 over square root of 1 over LC. That's one of our formulas for this series bandpass thing. This comes out of the review sheet, and it's in the book. So solve for L on this dude. This L is 1 over omega 0 squared C. It's 1 over 20 times 10 to the third, 20 kiloradians per second squared, 0.05 times 10 to the minus 6 microfarad. You end up with 0.05 Henry, which is a value we need for the time domain. This thing is, when we draw the time domain circuit, that's what that guy's going to be. So the next formula that we can use is this quality formula, which is the cutoff or the center frequency over the bandwidth. And we just calculated the center frequency, omega sub 0. So beta is going to be omega 0 over the quality. And the quality is given as 5. So omega 0 is also given as 20 times 10 to the third radians per second over 5. So it's 4,000 radians per second. That's an answer that we need for part B, bandwidth B, beta. And the last formula we have is for a series RLC bandpass filter. We have this beta equals R by L. And that's there's two different ones here. One for the series version, which is what we're doing, and then there's another one of these for the parallel. So this is the series only. Okay, just be careful on that. So the resistance is just beta L. It's 4,000 times our henries that we just calculated. It's my neighbor's dog name, Henry. He's barking. I can hear him right now. Anyway, so we have RLC time values, time domain values. So we could draw the circuit. Do we have that? We could, but the part B is also asking for these cutoff frequencies, which we don't have yet. So let's keep going. So from the text, there's this derivation the guy does where he gives you these omega C1, C2 formula. It's plus or minus R over 2L. This kind of thing that if you had to derive it on your own, it'd be like 3 days for you to figure it out. But he gives you this guy, and there's probably some significance to this. I mean, I'm sure there is, but it might show up later in the text as something more significant than it appears now. But anyway, there's this thing here which looks sort of semi-quadratic-y, and it'll give us our answer that we want. So this is plus or minus 200 over, because what's R? We just solve for R, and then we got our Henry. It's a nice dog, German Shepherd, about 2 years old, friendly. Barks a little bit too much sometimes, but he's okay. He's a nice dog. I like him. Anyway, this stuff. Just plugging in all of this stuff that we know into this formula that the author gives us. Just the 0.5 Henry, and then the 0.5 times 10 to the minus 6 cap. This one's just straight Henry, and this one's millifarad. Milli, right? Microfarad. And there's our Henry again, 200 ohms. And anyway, you get 2,000, plus or minus 2,000 plus root. And this stuff all works out well. 2,000 again squared. There's both 2,000s there, and this stuff ends up being 4 times 10 to the 8th. Just, showing the steps to show the patterns in the math, just in case that happens to be important later. Okay, so the two cutoff frequencies are off from this. This isn't the center. The center is, where's the center? Where is it? 20. It's exactly 20. But this guy is a little bit off from the center, right? Because the curve, which I'm going to draw very, 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 very shortly. In fact, I'll start it right now. I'll put it down here. The curve for this thing kind of looks like, it's kind of pointy on this side, and then it gets more not so pointy on that side. This is omega in radians per second. This is the bandpass attenuation diagram. So this is the magnitude of h of j omega, the magnitude of the transfer function, or the attenuation. We call it the attenuation from 1 to 0. At the two cutoff frequencies are at a value of 1 over root 2, which is exactly, which is not exactly, but it's exactly 1 over root 2, but it's approximately 0.707 if you like decimal numbers. And that gives you the two cutoffs. This is omega C1 and this is omega C2. Yeah. And because this thing is not symmetrical, the center frequency is not in the center. It's center in name only. It's actually more towards the left cutoff frequency, which you can see in these numbers. So it's 20 kiloradians per second, but now we got on either 2000 on either side of 20,099. Just off by a little bit. So anyway, omega cutoff 2 is 22,099 radians per second, and cutoff 1 is 18,099 radians per second. The center frequency is not in the center. Those are answers in part B. B asks for bandwidth, cutoffs, so those are them. And then for part A, they're asking you to draw the time domain circuit with all the component values. With these component values, capacitance, inductance, resistance. And that means, it looks like this. So Vi as a function of time, little v0 as a function of time is the output. This is a 200 ohm resistor. This is a 0.05 microfarad cap and the 0.05 henries. That was it. Yeah, it's just a bandpass filter. It's got the center frequency, which is not in the center, and then it's got these two cutoff frequencies, which are defined as the frequencies at which the attenuation is exactly 1 over root 2. So middle frequencies in between these two cutoff frequencies will be attenuated no more than 0.707. Low frequencies will get cut off, right? And high frequencies will get cut off. And the higher they are, the more they'll get cut off. And the lower they are, the more they'll get cut off. All right, we'll work another problem like this to sort of reinforce these same ideas and learn a little bit about how the phone works. So that's next. See you next time.